Welcome back to today's Explainer. I am so thrilled to have you here. If you're focused on truly mastering how things change rapidly in the real world, whether that's a bank account making you rich or a virus taking over a petri dish, you are in the perfect place. Today, we're going to unlock the mathematics behind these phenomena by exploring exponential growth and decay models. We're going to build a really solid foundation so that by the end of this session, you'll be able to read, write, and interpret these powerful mathematical models with total confidence. Okay, let's dive into our roadmap for today. We'll cover the exponential model explained, modeling a real-world context, distinguishing growth from decay, the dreaded percent decrease trap, a couple of knowledge checks and reasoning, and finally, a recap and transfer task to lock it all in. Section 1, the exponential model explained, decoding the formula. All right, let's start with our core concept and isolate the exact algebraic equation we use to measure exponential change. It's the fundamental structure of an exponential function. Y equals a times b to the power of x. So here's the crucial point. A represents your initial value. That's your starting amount before any time has passed. And b, well, that's your growth or decay factor. It's the multiplier that dictates exactly how quickly that starting amount changes over a specific unit of time. And that time, it's represented by our exponent x. Honestly, the fact that x, our time variable, is literally up in the exponent is exactly what makes this an exponential model rather than just a linear one. Section 2, modeling a real-world context, bacterial colony growth. Now let's look at a created context and see how this builds into a real-world scenario that we can track mathematically. Imagine a scientist peering into a microscope, observing a bacterial colony in a lab. The colony starts with exactly 100 bacteria and is growing at a steady rate of 5% each hour. It's kind of crazy how fast these multiply. So, to build our formula, we need our A and our B. Our starting amount, A, is simply 100. Now for B, we can't just plug in the number 5, and we definitely can't just plug in 0.05. Because the population is growing, it's actually retaining 100% of its original size and adding 5%. So we easily convert our 5% growth rate to a factor by just adding 0.05 to our base of 1. That gives us a factor of 1.05. This makes our final formula y equals 100 times 1.05 to the power of x. And this brilliantly illustrates how we calculate and interpret specific values as time goes on. At hour 1, we evaluate our function by substituting 1 for x, which gives us 105 bacteria. By hour 2, we plug in 2 for x, which basically means multiplying 105 by 1.05 again. We're already up to 110.25. Now, mathematically, sure, you get a decimal, but in a physical biology context, you'd likely just round that to 110 whole bacteria. The beautiful thing here is that you can literally see the compounding effect happening right before your eyes. Okay, we need to talk about the domain, which refers to all the possible input values for x. In a pure algebraic equation plotted on a graph, x can be anything, right? Even negative numbers. But when we're dealing with physical realities like living bacteria, our reasonable domain must be 0 or greater. Why? Because time simply cannot be negative. We start tracking the population at 0 hours. So we restrict our domain to x is greater than or equal to 0. Moving on to section 3, distinguishing growth from decay, analyzing the factor. We've looked at something growing, but what about things that are shrinking or decaying? What's really interesting here is how the factor b immediately tells us if our model is growing or shrinking, without us even having to plot points on a graph. If your factor b is greater than 1, your quantity is experiencing exponential growth. It's compounding upward. But if b is a decimal fraction between 0 and 1, it is experiencing exponential decay. It's constantly taking a fraction of the previous amount, so that curve drops downward over time. Section 4, the percent decrease trap, avoiding a common misconception. Now, let's tackle a very common mathematical trap that trips up a staggering number of students. When a word problem says a population decreases by 20%, your first instinct is probably to use 0.20 as the b factor. Actually, scratch that, it's completely incorrect. If you use 0.20, you are telling the formula that only 20% of the population survives each cycle. You must correct the misconception that a 20% decreases uses a factor of 0.20. Think about it. Because you are losing 20%, you actually retain 80%. Therefore, you subtract 0.20 from your baseline of 1, making your correct decay factor 0.80. Always, always focus on what is kept, not just what is lost. Section 5, knowledge checks and reasoning. Time to test your skills. All right, I'm going to give you 2 quick checks to ensure you've perfectly grasped these concepts. Take a look at this algebraic model.
y equals 500 times 1.12 to the power of x. I want you to identify two things for me. What is the initial value, and what is the exact percent growth rate? Take a mental beat. Look closely at the position of the numbers in the formula to identify your starting point and your rate.
Okay, let's break down the reasoning. Because a is 500, that's the number outside the parentheses, that is our initial value. Then we look inside the parentheses at our b factor, which is 1.12. Because it's greater than 1, we know for sure it's growth. The 0.12 attached to our baseline of 1 reveals the rate. To convert that decimal back to a percent, we just shift the decimal 2 spots, giving us a 12% growth rate.
Awesome. Let's look at check 2. We have a rescue shelter that starts with a population of 200 animals, and due to successful adoptions, the population decreases by 20% each year. I want you to write the correct exponential formula for this situation. Think carefully about the percent decrease trap we just discussed to formulate your answer. Let's break down the correct reasoning here. Our starting initial value, A, is straightforward. It's 200. Now for the rate. We dodged that trap perfectly by recognizing that a 20% decrease means we retain 80% of the animals from year to year. Subtracting 0.20 from 1 gives us 0.80 as our decay factor. Putting it all together, we arrive at y equals 200 times 0.80 to the power of x. If you got that, you are doing wonderfully.
Section 6. Recap and transfer task, bringing it all together. You've done incredible work parsing through these formulas today. Let's lock in everything we've learned with a quick 3-sentence recap. First, the equation y equals a times b to the x relies heavily on a as your absolute starting line and b as the engine driving the growth or decay. Second, you must always translate a real-world percent rate to a mathematical factor, strictly remembering that losing 20% means you use a factor of 0.80. And third, when applying these equations to physical, real-world contexts, a reasonable domain dictates that time cannot travel backward, making x strictly greater than or equal to 0. These 3 exact points are literally all you need to confidently conquer basic exponential modeling. Now for your transfer task to test your independence. If a savings account balance starts at $10,000 and grows at an annualized percentage rate of 4.25%, what is the exact algebraic formula? And what will that balance be after exactly 3 years? Grab a calculator and try to build the model yourself using everything we just went over. Are you starting to realize just how much of your financial future is governed by this single equation? I'll leave you with this final task to transfer your new skills to a real-world financial model. Good luck and keep exploring the math around you.